should probably start. Going live. Okay, great. So we seem to be live. So welcome to lecture 11. We will be expanding on our discussion from last time. So the agenda for today's lecture is to build these expanders that we have been seeing so far and come up with some fully explicit constructions of expanders, which are more or less from scratch. I mean, like the analysis, everything will be extremely elementary. And hopefully I'll also show you how powerful these things can be. I mean, we've already seen plenty of examples in randomness reduction. I mean, the randomness reductions in sort of BPP and RP algorithms and stuff like that. And these are just extremely useful objects to have with us so that, I mean, for a variety of applications. Okay, so let's just do a brief recap. So I don't know if this notation was ever used so far. So I'm going to start using this notation of ND lambda expanders, which is to mean the following, that it's a graph it's an undirected graph on n vertices, and it is deregular. In this course, we'll only be dealing with regular graphs so that, a lot of calculations become simpler. And then the second largest eigenvalue in absolute value is lambda. Okay, so this is just a notation for it. Ideally, we would want n to be large, d to be small, and lambda to be as far away from 1 as possible. We want the gap from 1 to be large enough. Okay, so that's the goal. And so that's what we'll call a spectral expander. But I'll end up dropping this word spectral because this is what we'll be dealing with throughout. Okay, and just to keep in mind that lambda of G, one definition, which will be useful, is that you look at all possible vectors that are perpendicular to your stationary distribution. And when we are dealing with undirected graphs that are deregular, the stationary distribution is the nice, basically uniform distribution on all the vertices. So you can mentally tell yourself that whenever you see this pi, I mean, it's just the 1 by n, blah, blah, blah. Okay, that's the vector that you have. And you look at the probability, I mean, the distribution after you apply x, and you look at the norm with respect to what it was to begin. So you're basically asking how much does the action of random walk shrink vectors that are orthogonal to the stationary distribution. Okay, and I guess I should also apologize to people who are used to putting matrices on the left. So I mean, we'll have to come up with a compromise one of two things. Either if you want to apply one step followed by another step followed by another step, would you like to write the matrices one after another on the right, or would you be okay with putting the vector, at whatever? So you need to make a compromise somewhere. We have chosen to make the compromise by making sure that when we're applying multiple operations, we just write matrices one after another on the right. Okay, but since we are dealing with undirected graphs that are deregular, etc., we'll always be dealing with matrices that are symmetric. So, I mean, I could have just, replaced this with mx and nothing really changes. But I think it's just a good, you just decide on one sort of consistent notation and just stick to that, because in situations where the matrix is not symmetric, etc., which is a typical case when the graph is not regular, this distinction becomes important. But in this course, it will actually turn out to not be the case because we will always be dealing with regular graphs. So this will not be a problem. But I'm still going to stick to this notation so that, the next time you encounter those things, it becomes easier for you. Okay. And the spectral gap, which is the difference of lambda G from 1. Like how far away from 1 is lambda G. And intuitively, this gives a sense of how sort of well connected the graph is. And so that's roughly our mental picture of what the spectral gap is supposed to denote. Okay. And we saw that spectral expanders immediately give vertex expanders. And in fact, the converse is also true. There is some loss in parameters if you go this way and come back. But morally speaking, these are all the same kinds of objects. And spectral expansion is just it's a lot more convenient to work with because, these are all discussions that we had last time, that vertex expansion looks like an NP sort of statement and so on, whereas spectral expansion is something which is like calculation of eigenvalues and just checking something, which is a poly-time computation. Okay. And like whenever you encounter spectral expansion and random walks and what happens to random walks when you take, and so on. The standard way most of these proof templates will go is like you start with your probability vector. This is the distribution you currently have on your vertices. And you want to know what happens to this distribution after you take one step in the random walk. And typically the way you do this is you replace your probability distribution by the parallel component and the perpendicular component. By which what I mean is the parallel component is like basically along the direction of pi, that is along the stationary direction. And the perpendicular component happens to be whatever is perpendicular to pi. Okay, perpendicular to pi. So you just decompose your whatever the probability vector into these two components, and you just look at the operation of m on those two components separately. Okay, by the definition of pi, so when I look at pi plus p perp, by the way, if p is a probability distribution, it turns out that this p parallel will be exactly equal to pi rather than a constant multiple times pi. Okay, if you just work, because this must sum up to 1, this is also summing up to 1. So therefore, it will turn out that the dot product is just 1, depending on what dot product you choose. I mean, these are all things that you hopefully, I mean, like with a little bit of tinkering, you can just convince yourself that it's true. So now what happens when you apply an m? So this just becomes pi m plus p perp times m. And pi m by definition is pi, because that's what the stationary means. And this p perp times m is what you mentally want to think of as the error. And you would like this error term to quickly go to 0. And that's the reason why this lambda g is an important thing to keep in mind, because it sort of tells you, in comparison to what you started off with, is your error term smaller at all? I mean, are you getting closer and closer to pi in some sense? Okay, so that's roughly what we were saying. And the spectral expansion basically tells you that this is lambda factor smaller than, it's smaller than p perp itself, which in particular means it's smaller than p. Okay, so that is typically how these sort of calculations proceed. And we took a typical such calculation and we wrote down what is called this matrix decomposition last time. Okay. Okay, we wrote down this matrix decomposition last time, which is that whenever you have a random walk matrix that corresponds to a lambda expander, you can decompose this random walk matrix into 1 minus lambda times j, where j is basically the matrix where all its rows are pi. Okay, which in our case means it's a matrix that's made up of 1 by n everywhere. Okay, in the undirected regular case. Okay, so it's made, you can write it as 1 minus lambda times j plus some lambda times e, where e is some error term, and e is something that has spectral norm 1. What do we mean by this? E doesn't expand any vector. So x times e will be no longer than the norm of x itself. So, and this lambda factor is sort of saying that, you know, when you look at lambda times e as an error term, then no matter what vector you feed in, it will shrink the vector by a factor of lambda. Okay, so this is roughly what it means. And yeah.
No, just the vector decomposition and the matrix decomposition are not the same. They are two different.
Yeah, I agree. They're two different things, but basically inspired by this, because this is the sort of decomposition we kept doing a lot of times. It also helps to look at the matrix decomposition, which is not exactly, you know, the same as the vector decomposition, but it gives a good picture of what is happening. Because mentally, what I like to think of is like, this is the random walk matrix of the complete graph with self loops on every vertex. It's like when you, if you are at a certain distribution, if you're at a certain vertex, all other vertices are equally likely. Right? It's just a random walk matrix that corresponds to this, the best possible expander, so to speak. Okay, plus an error term. So intuitively, what I want to say is that whenever you have a lambda expander, I would mentally want to think of, I would mentally say that you should think of it as saying, basically with weight 1 minus lambda, it behaves like a complete graph. And with some lambda, it does something nonsensical. And hopefully that nonsensical thing is something that you can tolerate. And and this is, there will be a lot of applications where this sort of mental model helps a lot. Okay, good. So what are we interested in finally? We saw lots of applications of these things. Now, what we want is not just one graph, which happens to be an expander, but we would like to have a family of graphs, wherein I just give you a sequence of such graphs. I mean, if I'm truly this thing, I should be putting in my whatever lambda expander, where I goes from 1 to infinity. Okay, such that these graphs are on larger and larger number of vertices. Hopefully, I want them all to be d-regular for some fixed constant t. And I would like them all to be a lambda expander for some fixed constant lambda. I mean, I'm interested in a certain expansion. I cannot tolerate more than a certain degree. You give me graphs on larger and larger number of vertices. This could be a possible goal. Okay. And now there are two possible models here. One is the mildly explicit version, which is, okay, what do I mean by I give you a graph G? One possibility could be that I can just write down this graph completely. Like I'll write down the adjacency matrix of the graph to you in polynomial and n time. That is a number of vertices many. That is one version. But there were some applications that we saw where this was actually something we could not afford, because we are interested in graphs that are on exponentially many vertices, and I can't afford to spend time exponentially to write down the graph or something. But maybe what I'm really interested in, I don't care about the graph in its entirety. All I want is the following. If I give you a vertex u and I ask you for, let's say, the 7th neighbor, can you tell me what the 7th neighbor is in polynomial time in the description of my input now? My input only consists of a label for a vertex and a label for whichth neighbor I'm interested in. So the input is log n and log b. That's the number of bits that it has. So I only want to run, I'm only interested in graphs that can give this operation in poly in log n comma log d. And in such cases, we were saying that these graphs are super explicit, and sometimes they're called fully explicit or strongly explicit, etc., etc. Okay. And this is what we will be dealing with today. And we saw that one of the key applications of this was to do error reduction using far fewer randomness than just typically repeating it, like, on independent tries and so on. Okay. So the focus of today's lecture is going to be, are there explicit families? But I mean, one could say that, well, we already saw that there are explicit families last time, in the sense that there were these Margulis constructions that we saw from last time. That this is some vertex set, and these were the neighbors of any vertex a comma b. Okay, and the theorem of Margulis, and it was simplified later by Gaber and Galil, showed that the spectral gap is something. That is, there is some fixed constant such that lambda is 1 minus that constant. Okay, so this is what we saw this, but of course we didn't prove that this was the case. So this is an explicit construction, but the proof is not explicit. I mean, the proof is a little complicated. We saw another example, which was a really, really simple description of a graph, which is you just take your vertex set to be all residues modulo a prime, that is 0, 1, 2, 3, all the way till p minus 1. And you connect vertex u to u plus 1, u minus 1, and u inverse. And whenever you see a 0 and you want to compute 0 inverse, you just say, okay, 0 inverse is itself. Okay, it's just some, I mean, you're coming up with some graph. And this also turns out that there is some spectral gap. There is some fixed epsilon greater than 0, such that for all choices of primes p, this happens to have like the lambda is like 1 minus epsilon. Okay, so these are some examples that we saw. And then we also briefly spoke about what is the best that one can hope for. We are trying to somehow construct a constant degree expander and try to make lambda as small as possible. So one question that you should be asking is, okay, what's the best lambda? I mean, when would I know that I have gotten close to the best thing? Okay, and in that regard, a good heuristic to always have in these pseudorandom constructions is to ask, what do random graphs give us? Like, it's like a good benchmark to have. Okay, the whole point of this course is that we are trying to build objects that look random. So let's ask ourselves, what do random graphs give us? And this, I think we briefly mentioned that lambda of g for a random graph turns out to be something like at most 2 square root d minus 1 over d plus little o of 1 or plus order 1.
Little o of 1, where the little o depends on n.
Oh, yeah, the little o depends on n. Something. It's basically 2 square root d minus 1 over d plus some chiller. Okay. On the other hand, for any d regular family, there's also a lower bound that says that lambda of G better be at least as large as 2 square root d minus 1 over d minus order 1. That is, I mean, no matter what infinite family you pick up, your lambda has to be larger than essentially 2 square root d minus 1 over d if you make some minor corrections or something. And random graphs come pretty close to that. They more or less achieve this.
This is also little o. This is also little o n.
Oh, I somehow thought one of them was a constant.
No. Both of them are little o. Both of them are things which go to 0 as n goes to infinity.
Oh, okay.
Capital N goes to infinity.
Okay. Okay. And turns out that there are these graphs that are called LPS graphs by Lubotsky, Phillips, and Sarnak, where this lambda of G is actually equal to 2 square root d minus, sorry, this is less than or equal to 2 square root d minus 1 over d. So which means they actually perform a little better than random graphs in the sense that they don't even have this chiller factor. Okay. And graphs that satisfy this bound, they are also called Ramanujan graphs. I mean, the name Ramanujan graphs itself is a funny name in the sense that Lubotsky, Phillips, and Sarnak proved this eigenvalue bound via certain Ramanujan conjectures. And so in principle, it should have been the case that graphs where the eigenvalue bounds you prove using these Ramanujan conjectures maybe are called Ramanujan graphs. But at this point, it's just basically any graph that sort of achieves eigenvalue, which is this, they are called Ramanujan graphs. Okay, it's just the nomenclature is slightly different, but this is what it is. Okay, so what I want to do is now the following, which is like, it's like this way of saying, I've just shown you that these expanders are like stars and they're like awesome things to have. And there's a question of, are there stars in this world? And I've shown you a bunch of stars. But I guess what we might want to do is like, can we become a star? Like you start off with a stupid graph, which is not really a good expander or something. But can I somehow make it better? And, can I start with an arbitrary graph and slowly improve its expansion so that I end up getting an expander family? Okay. And this perspective will be particularly important in the next lecture. But so this is the mode that we're going to work with today. Today, what we're going to do, we're just going to start off with some completely crazy, I mean, any deregular graph that you want with, and we'll slowly keep improving this graph so that we end up with an expander family. Okay. So that's going to be the goal. Okay. So, okay, let me just briefly, okay, now before this, okay, no, okay, so here is the goal. So, okay, so what we're going to do is we're going to just start with the graph and keep applying certain operations on it to improve it in certain aspects. Okay, it will be useful to have some notation. So whenever I have an n comma d graph, by that I mean that it's an n vertex deregular graph. They're always undirected. Okay, we'll use the notation gamma of u comma I to just refer to what is the ith neighbor of u. Okay, so I'm expecting I to be somewhere in 1 all the way till d, and u is one vertex label, and this is just going to tell you what is my ith neighbor. Okay, so let's say the answer to this was some v. Okay, now it must also be that because u is connected to v, I mean v is also connected to u. So it must be the case that gamma of v comma j is equal to u for some j. Right? So in order to mix both of them together, what we'll call is what's called the rotation map of G. We'll say gamma of u comma I equals v comma j to indicate that the ith neighbor of u is v and the jth neighbor of v is u. And in the words of Jaikumar, this j is like a hum aapke hai kaun sort of thing. So you're trying to sort of say from the perspective of v, which its neighbor is u. Okay. So this is something that will be very useful to keep in mind, in the sense that because this is what we really want to build efficiently. We'll tell ourselves that a graph is explicit if this rotation map can be computed efficiently. Okay.
Hi, I have a question.
Yeah.
So when you say ith neighbor, does it mean the neighbor at distance I, or you
No,
have
no.
numbered
So
neighbors in
we'll just assume that every vertex, the d edges that go out of the vertex, this vertex has labeled those d edges by saying this is my first edge, second edge, third edge, etc. And when I mean the ith neighbor, all I mean is if I take the ith edge out of me, which vertex do I land up?
Okay.
Okay, so that's what this means.
In some sense, we're not only constructing a expander graph, we're also constructing a labeled expander graph in which every edge is around every vertex, all the edges are labeled 1 to d. And this could be an arbitrary labeling.
Yeah, I'm not insisting that u's label and v's label must be consistent in some way, nothing. Like there are d edges that were going out of u, and you decided to call them 1, 2, 3 all the way to v. Similarly, v might have a different numbering there. And the rotation map is basically saying if I take the ith neighbor out of u, I end up at a vertex j, but I end up at vertex j using its jth edge or something, right? So you're keeping track of both this information.
Okay.
Yeah. Okay. Cool. Okay. So now what we are going to do is we are going to basically try and make changes to the graph that somehow modify either the number of vertices or the degree or the eigenvalue. And the hope is that we can put together these operations to get what we want. Because we are trying to come up with some way in which this d stays small, this lambda is made better and better, by which I mean it moves closer and closer to 0, and this n becomes larger and larger. This is what we are trying to achieve. Okay, because we are trying to build this family of expanders on more and more vertices, but the degree stays small and the lambda stays small. Okay.
You're the one who said who would use gamma for a neighbor in the.
Sorry? No, that is true, because I can't use n, because n is going to be used for the number of vertices.
Yeah.
So you have to make some concessions somewhere. So,
Okay.
yeah. Okay. So the first thing we are going to do is probably what I think is the most natural operation to try, which is what is called the graph G squared. Okay. Okay. So what is the formal definition of what G squared is? So for every length 2 path in G, and by the way, I'm not insisting that this path needs to be simple or anything. The path could just be U, V, U. That is a valid length 2 path. Basically, take an edge out, take another edge. So U, V, and W, I'm not insisting they are distinct vertices or anything of that sort. So for every such length 2 path, I'm going to put an edge in G squared connecting U and W. Okay. So I hope the definition is clear. So every edge in G squared corresponds to a walk of length 2 in G. Okay. So now can someone tell me what the degree of this graph should be? Firstly, is this a deregular graph? We started off with a G being deregular. Oh, sorry, is it a regular graph? We started off with the G being regular. Is the graph now still continuing to be regular?
Be like d squared.
Right. So the degree here has to be
Maybe a bit less than that.
No, in fact, it will be exactly d squared because I have d vertices coming out of U. So I have d choices for the first edge. And then I have d choices for the second edge.
It's not a simple graph anymore.
It's not a simple graph. There will now be self loops. There might be multiple edges between 2 vertices or something. But every edge in G squared corresponds to one length to walk in G.
So by degree, we are not saying number of neighbors, but number of edges.
Number of edges emanating out of that vertex. That's what I mean by that. And if you want to write it in terms of this gamma map, okay, so gamma G squared of U comma ij. Now you can think of all the edges out of this vertex U in G squared as being labeled by a tuple. Okay, So this is just going to be, let's first take gamma g of u comma I. Now we would have landed up at some vertex v. And now I take the, whatever, the jth neighbor of that. So this is just saying, I first take the ith neighbor of u, followed by the jth neighbor of wherever I landed. I mean, if I landed in some vertex v, I take the jth. That I'm going to call the ijth neighbor of this vertex u now in the graph G squared. Okay, so okay, what's the simplest way to keep switching between these things? Okay, just one second. I'm going to start. I'm going to show you just some demos. Is this visible?
Yeah.
So the notebook is visible, right?
Yes.
Okay. Okay. So this is just a Jupyter, I mean, like a notebook where we can just run all of these things to just get our hands dirty. So this is just the 7th cycle I have written. So this is like saying that the vertex 3, the 0th neighbor is 4. So it's like 1 above, and the 1th neighbor is like 1 below. So it's like 4 and 2. And if we draw it, I mean, like we get the cycle like this. Okay. And similarly, there are these Selberg graphs and whatever, Margulies and so on. I just want to go to the squaring thing. And these are LPS graphs. You can imagine LPS graph. I mean, it looks so kachamucha something. Okay. So now let's look at graph powering. So I start with a cycle, which looks like this. But if I look at G squared will start looking like this. Because 1 is now connected to 3, because there is a path that would have gone 1, 2, 3 in the previous case. And there are now self loops on every vertex, because I could have gone from 2 to 3 and 3 back to 2. So that would result in a self loop. In fact, there are 2 self loops there, though the picture doesn't show this, which is that there's another self loop, which is like 2 going to 1 and then back to 2. So this actually happens to be a degree 4 graph. Okay. So,
but in the gamma notation, like, so gamma g square of I comma I would assign the same self loop, right, for both.
So sorry, just one second. Let me just okay. Apparently, I have to stop sharing here in order to go back to my thing. There should probably have been a better way of doing it. So gamma of I comma I, for instance, okay, could just mean that, by the way, my screen is visible. Yeah, will just mean that you take the ith neighbor of u. If that happens to be a self loop, then you will stay back in u.
No.
And then sorry?
No, so G doesn't have, let us say G is just a de-regular without any self loop, right? So
okay, so then gamma of u comma I will end up going to some other vertex v.
Yes.
Okay, and it depends on what the jth neighbor of that vertex is. If that happens to be u again, you now end up with a self loop.
No, that is true, but I was asking, like, on your LHS, if I equal to J, or I don't know, like, depends, I guess depends on the labeling of the vertex and all.
That's
that,
right. That's right. It could be the case that if u's ith neighbor is v, and v's ith neighbor is u again, then u of I comma I will end up giving you u again.
In particular, if rod g ui is equal to j, then this will be a self loop.
So basically, let's just write this out. If rod g of u comma I, if this was equal to v comma j, then gamma g squared of u comma ij, this will be equal to u.
My question is, does it distinguish between all the self loops, or are all the self loops collapsed to just one?
No. It keeps track of different self loop as a different thing. A vertex only knows I have d edges emanating out of me. I mean, the vertex will not be aware of if some of these d edges end up going to the same endpoint. So it's going, if there are multiple self loop, it will just think of each self loop as a separate thing. Like this is one edge emanating out of me, this is another edge emanating out of me. It may be so happens that both of them get back to me.
Okay.
But I'm not going to distinguish. I mean, I'm going to keep them as separate as possible.
So think of it not as the adjacency matrix, but as an adjacency list in which you have For every vertex, you have d neighbors in sequence.
Yeah, did that answer your question?
Yeah.
Okay, good. So now let's ask the most important thing, which is what is lambda for G squared? Or I should have probably put what is lambda of G squared. Okay, in order to understand this, maybe a simpler question to ask is, do we know what the random walk matrix is? Like if I wanted to take one random step in G squared, what is its relation to my original random walk in my graph G? Okay, and hopefully, I mean, since you didn't you didn't object to the fact that I called this G squared, I mean, that's already sort of giving you a hint of what this should be. And it's easy to observe that this is actually, if MG is the random walk matrix for G, then the random walk matrix here is just G squared. Because what is a step in G squared? You take one step in G followed by another step in G, and you end up with wherever you end up. So the random walk is just the square of whatever you have. So since the random walk is the square, what can we now say about lambda of G squared? Okay, let's just look at the definition. What is lambda of G squared? This is going to be, you look at the max of all x that are perpendicular to the stationary distribution, and you look at x, xm squared over x. Like how much is the vector shrunk? Okay, but I know for a fact that, so, I mean, this, like, let me write it as mmx. I know the first operation mx will already shrink that vector by a factor of lambda. And now the second operation mx will shrink it by another factor of lambda. So this is just going to be at most lambda times max x perpendicular to pi of and this is like lambda squared. So I hope this is okay. I mean, there are probably many ways of seeing it, because anything that was an eigenvector for m continues to be an eigenvector for m squared. It's just that the eigenvalues all become squares. So whatever was away from 1, I mean, now it's going to be, I mean, that's going to be like lambda squared. Okay, so I'm sort of cheating a little bit here. All the eigenvalues get squared. So if the spectral gap was something, then the spectral gap becomes now larger, because all eigenvalues get closer to, what should I say? They all get closer to 0. Okay, so I hope this is reasonably clear. And let's just summarize.
Convince yourself actually it's equality.
Yeah, and I was, yeah, okay. Actually, you can convince yourself that all of these are equalities by feeding in the right eigenvector. The equality will be achieved at the right eigenvector. So what are the pros and cons of this operation? So the first thing is, the big pro is that lambda has now become lambda squared. And notice lambda was a number between 0 and 1. So the square of a number is like much smaller than what you started off with. So it's amazing at bringing lambda down. So it helps improve the spectral gap. Okay, it didn't really change the number of vertices. The number of vertices stays whatever it was to begin with. The graph is still on the same set of vertices. But a bad thing was that we brought lambda down at the cost of increasing d. And we are trying to somehow get lambda down and at the same time keep d what it was, or not increase it by too much. But right now this is increasing d. Okay, so that's the what this operation does, the pros and cons of this operation. So in general, this thing is called graph powering. I mean, you can imagine what g power 10 means. Every edge in g power 10 corresponds to a 10-step walk in the graph G. And the random walk matrix will be m power 10. The eigenvalues will all become lambda power 10, etc., etc. So this in general is just called graph powering. Graph powering in general will not change the number of vertices, but it will bring down lambda at the cost of increasing the degree. So are there any questions so far? Okay, good. If there are no further questions, let's move on to the next operation, which is going to be, now I have two graphs, which I'm going to call, one is an N1 D1 lambda 1 graph, and the other is an N2 D2 lambda 2 graph. And I'm now going to build this weird G1, whatever, circled X or something. Okay, I'll just use the word. I'm going to call it G1 tensor G2. Okay, which is the graph whose vertex set is basically all pairs of vertices, one from U and one from V. So I'm just denoting this by N1 cross N2 to just means that they're all pairs of vertices where the first coordinate comes from U and the second coordinate comes from V. Sorry, first coordinate comes from G1, second coordinate comes from G2. Okay, now what do? I will connect U1 V1 to the pair U2 V2 if U1 U2 is a legitimate edge in G1 and V1 V2 is a legitimate edge in G2. Okay, so I hope the definition is clear. We are going to end up connecting vertex U1 V1 to U2 V2 if the first coordinates are adjacent in the first graph and the second coordinates are adjacent in the second graph. Again, I'm cheating here. What I really mean is the following. Every vertex U1 V1, there are going to be edges emanating out of it for every labeled edge out of U and every labeled edge out of V. And when I ask you to take the 3,4th edge, what I mean is you look at the 3th neighbor of U and the 4th neighbor of V. That is, you move on both graphs. So I hope the definition of what this tensor is clear. Okay, so let's just look at some basic operations. What is the degree of this graph?
D1, D2.
Yeah, so now the degree would basically be, I have D1 many choices for the neighbors out of U and D2 many choices for the neighbors out of V. So these are the number of possible edges that I can take out of this pair. Okay, because I would like to think of the edge labels as being I comma j, where I belongs to D1 and j belongs to D2. Okay, so hope that is clear. And the most important thing to try and understand is, what about the eigenvalues? What happens to the eigenvalues? Something that I just ignored is that the number of vertices is now N1, N2. Right? So we seem to have made some good thing in increasing the number of vertices, but we seem to have paid for it by increasing the degree also in the process. Now the hope is that we didn't do something bad to the eigenvalues. So the next thing that we want to ask is like, what is the eigenvalues of this, of this new graph? Maybe to understand that, maybe a better thing to ask is like, what is the adjacency matrix? Okay, maybe if we understand the adjacency matrix better, then we may understand the eigenvalues better. So I'm going to again share screen and show you, show you an example. Sorry, I should choose the desktop. Okay, I hope my screen is visible. So this is what tensoring is going to be. So I'm just going to take the Selberg graph, which is some 5 vertex graph that has an adjacency. Yeah.
Are you sharing?
The PDF is obstructing the.
Oh, sorry, one sec. Is it visible now?
Yes.
Oh, okay, good. So yeah, so the Selberg graph, this is what the adjacency matrix looks like. Okay, it's some weird adjacency matrix. So now let's look at the 4 cycle, and the 4 cycles adjacency matrix looks something. I mean, we know what the 4 cycle looks like. Now let's take the tensor and look at the adjacency matrix. Now at the moment it looks like some weird blob of, it's a large adjacency matrix, etc. But it will be convenient to just print it in blocks in a slightly different structure. The moment you do this, you seem to get a slightly different picture. So there are some blocks that look like something, but there are many other blocks that look like zeros. Okay. And in fact, all the somethings that you see, they're all the same something. Okay. And what is this? This just happens to be the adjacency matrix of the cycle. If you look at a single block, like 1 is connected to 2 and 4, and 2 is connected to 1 and 3. 3 is connected to 2 and 4, and so on. So this is just the adjacency matrix of a cycle. Okay. And if you look at which all blocks are, like, let's look at row 1. It looks like there's a non-zero block, 0, 0, and a non-zero block. And if we go back to what the adjacency matrix of the Selberg graph was, it was 1, 1, 0, 0, 1. Okay. And similarly, if you look at the third row, it looks like 0, 1, 0, 2, 0. So let's look at the third block here. It's going to be 0, adjacency matrix of cycle, 0, 2 times the adjacency matrix of cycle, and 0. Okay. So the adjacency matrix of the tensor product seems to have this nice decomposition where you took the adjacency matrix of the old graph, and in every entry, you blew it up to an adjacency matrix of this, whatever you tensored with. So that's what really has happened here. You basically took the 5 cross 5 adjacency matrix of the Selberg graph, and in every entry, instead of a single value there, you just replaced it by whatever that value was times the adjacency matrix of the cycle in the case. Okay. Now the point is, this should make sense. I mean, like in hindsight, once you see this, this must be completely natural as to why the adjacency matrix should look like this. Okay. So, okay, now therefore let me stop sharing screen, go back here. Okay. Okay. So let's look at what the adjacency matrix looks like. I'm going to just, the rows and columns of the adjacency matrix are labeled by vertices, but let's call them u, 1, u, 2, blah, 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 till u, whatever the number. I mean, if this is going to be what, n2. Okay. And similarly, this is some v, 1, or okay, let's say u prime, 1, blah, 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 till u prime, n2. Okay. When will we put an edge between, let's say, one of these vertices and one of these vertices? If and only if, firstly, u must be connected to u prime. If u is not connected to u prime, this is going to be the 0 block anyway. But if u is connected to u prime, then basically what you see in this block is just a connectivity property between whatever happens inside the graph H. So it makes perfect sense that this is what the adjacency matrix should look like. The adjacency matrix should look like you just took every entry and just blew it up by the matrix corresponding to H. So, okay. And in fact, this is actually, I mean, the adjacency matrix happens to be the adjacency matrix of AG, tensor product, the adjacency matrix of AH, where by, I mean, the definition of what a tensor product of 2 matrices are is precisely this thing. Okay. Where like replace every entry, whatever, AG, IJ, by AG IJ times H, oh sorry, times AH. Okay, so that's what the matrix looks like. So okay, great. We have now understood what the adjacency matrix looks like. We still need to figure out what are the eigenvalues of this.
So one question. So
yeah,
in the adjacency matrix, there were some entries like 2 and all. So
that's right.
Yes, so I'm not able to see.
So basically the point is, what does there being a 2 between this mean? It means that there u has 2 edges that both land up at the vertex V. Right? So we want to say, therefore, if u1, I mean, if 1 was connected to 1 in the graph H, then there should be 2 paths from u, 1 to u prime, 1. Because there are 2 possible edges out of u that was going into V. And I want to keep that information with me. Did that make sense?
Yeah, okay.
Yeah, so which is why the adjacency matrix is somehow collapsing and saying how many neighbors of u is equal to V. I mean, typically we think of adjacency matrix as just saying whether there is an edge from this to this. You can think of it as maybe you put a weight on an edge if you want, but I think it is convenient to just think of them as separate edges that are going on. So as you can imagine, if there are 2 edges from u to u prime and 2 edges from 1 to 1 in the graph H, now this entry would have been a 4. Because there are 4 ways to go from u1 to u prime. Okay, good. So tensoring roughly refers to you just taking steps in parallel. Like every step in the graph G tensor H corresponds to taking a step in G and a step in H, and then you just write them both as 2 separate vertices. Okay, so that's what tensoring refers to. And here is just a pictorial description of what tensoring is. I don't know if this is insightful, but yeah, I mean, if you take a tensor of a triangle with something like this is what ends up happening. Something, you get some graph. I mean, I don't know if it's helpful. But here is a useful question to know. Now, just like we talk about tensors of 2 matrices, you can now talk about tensors of 2 vectors. I give you, think of a vector as just a 1 cross n matrix, and this is another 1 cross n matrix. This is the same thing as saying you just every entry you are going to blow it up by a copy of V scaled up by the corresponding entry, etc. Okay. So here is an exercise. If you haven't seen this, I think you should definitely try it out. Okay. If you aren't convinced of this, you should try it out. But I'm hoping that all of you should be able to guess what the answer of this should be. I mean, if there is any justice in the world, what would the answer of U tensor V, I mean, when acted upon by A1 tensor A2, what should you expect it to become?
A1 U tensor A2V.
Exactly. So it's just like, the whole point of doing things in parallel is that you can think of them as 2 separate things that are happening. So this just turns out to be UA1 tensor VA2. Okay. And I'll insist and say, check this. Okay. It gives you these are sort of things that you do it once, you're convinced of it, and then you can just, some of the mental picture of taking steps in parallel just stays with you and you can move on from there. Okay. Now, therefore, a corollary of the above observation is that suppose U happens to be an eigenvector of A1 with eigenvalue alpha, say, and V happens to be an eigenvector of A2 with eigenvalue beta. What would happen if I looked at U tensor V applied on A1, A2? I will end up, as we just said, I will end up with UA1 tensored with VA2, which in this case will just become lambda, I called it alpha. So this is like alpha times U tensor beta times V. I can just pull this beta out. So you basically get alpha beta times U tensor V. So this is saying that if U and V are eigenvectors, then U tensor V is an eigenvector of A1 tensor A2 with eigenvalue alpha beta. Okay. So if you have worked this out, this will be an immediate corollary. Since we have this, we now know what the eigenvectors of U1 tensor U2 are. If I know the eigenvalues of the graph G, and I know the eigenvalues of the graph H, I know the eigenvalues of the graph G tensor H. They're all possible products between them. Okay. So now here is a question. I should not have, this became a spoiler thing. Okay. So now we know that G1 tensor G2 is a graph on N1, N2 vertices. It has degree D1, D2. What is unclear is what is the eigenvalue? What is the second largest eigenvalue of G1 tensor G2? What are all the eigenvalues of G1 tensor G2? There's one corresponding to 1 times 1. The eigenvalue 1 of G1 times the eigenvalue 2 of G2. Then there is something that looks like 1 times lambda G2. And there's one that looks like lambda G1 times 1. I don't know which of the two is the larger of all of them. So, but nevertheless, you can basically say that this is at most max of lambda of G1 and lambda of G2. Okay, so I hope this was clear. It just follows from the fact that the eigenvalues of this new matrix are all possible products. There is certainly a 1, which was a 1 times 1. So nothing really changed there. But there was a 1 times lambda 1, and then there's a 1 times lambda 2. I don't know which one is larger, but whichever was the larger is the larger eigenvalue. Okay, are there any questions? If there are questions, please interrupt me. Yeah.
In whatever you have said so far, it is true for even the normalized adjacency.
Yeah. So it's just that because the normalized adjacency matrix of a whatever graph 1 is that by D1, and this is that by D2. So you get a nice 1 by D1, D2 like you would expect.
No, but what if it is not deregular? Like I think the earlier theory.
Yeah. So I mean, which is why I'm sort of simplifying here and saying that, we are working with deregular graphs. But if it is not deregular, then the normalized adjacency matrix itself is not the right thing. You should be looking at the random walk matrix. And the right way of saying that the random walk matrix of the tensor product is the tensor product of the random walk matrices. Yeah. So then there is not a global normalization factor. The one needs to be a bit more careful. Okay, great. So what is this roughly saying? It's saying that we can increase the number of vertices. Like, yay, okay, we've figured out how to do that now. But again, we are paying in the degree. The degree is becoming larger. This is something that we didn't want to. And in terms of this is like saying that the new graph is no worse than the expander, no worse of an expander compared to the graphs you started off with. Like whichever was the worst expander, this is just as bad as that. So you haven't done much with respect to improving lambda at all here. But on what we do seem to have done is increase the number of vertices. Okay. So since we saw one where we could improve lambda, and we have now seen one where we can improve the number of vertices, the missing link is how the hell do you reduce the degree? Is there a way in which we can reduce degree without hurting lambda too much? Okay, so we need to come up with graph operations that somehow result in the degree being smaller. Okay, and so this is what we want to mainly solve. Like, how do you somehow reduce the degree without losing too much in lambda? Okay, so there's something called the replacement product. It's quite a nice product. It's just painful to analyze. But if you're really interested in, there is one of the exercises in Vadan's notes is precisely to analyze the replacement product. So I will just tell you very roughly what the replacement product is. If you're interested, you can look at the notes. So just think of it as saying, let's say this is my graph G and it was, I don't know, 5 regular. Okay. The replacement product of this with a 5 cycle, I'm going to roughly denote by this. Okay, so I'm going to copy this and paste it here. So what you do is the following. Okay, just think of, you just erase off this vertex and think of this as a cloud. Now there are actually 5 vertices that are sitting in that cloud. And you put a copy of this graph on those 5 vertices. So in this case, it's going to be a 5 cycle. Okay, it's not quite as simple as this, but this is like intuitively what happens in a replacement product. You basically imagine sitting on a vertex. There are 5 edges going out, and you basically give the responsibility of each such edge to one vertex of this inner graph and connect those vertices according to whatever this inner graph is. Okay, so as a result, what happens? The number of vertices is now n1 times n2. So by the way, replacement product is valid only when this looks like an n1 n2 comma lambda graph, and this should look like an n2 comma whatever d comma lambda graph or something. That is, the number of vertices of the second graph should match the degree of the first graph. That's when this replacement product makes sense. So what you can now observe is that right now this is a 3 regular graph, because there are whatever there was a deregular component corresponding to the inside the cloud, and there is one edge going out. So the degree happens to be d2 plus 1 if you care about it. It's just that analyzing lambda is painful. Okay, so we are not going to do this. We're instead going to deal with another product, which is just much easier to work with. It feels a little mysterious, but hopefully after today's lecture, it will seem very natural. Okay, so yeah, and one of the disadvantages of this is that a random walk in this new graph, it basically prefers the cloud too much. Like most of the edges will be within the cloud. There's just one edge that is taking you from one cloud to another cloud. So that is one reason why it's not a great product, but nevertheless, we'll do the following. So, okay, so what we are going to do is we're going to come up with a graph that is often called a G1 circled Z G2, and because it's called the zig-zag product, and this is the main innovation in this thing, and I'm going to tell you how the zig-zag product works. Okay, like in the replacement product, it is important that the number of vertices of the second graph equals the degree of the first graph. So this D and this D should match. Okay, so here is what the zigzag product is. Okay, I'm going to pictorially represent the zigzag product of some graph G whose edges are these dotted edges. Okay, it's some 6 regular graph. I don't care what's happening outside of this. And I'm going to take a zigzag product of that 6 regular graph with this whatever graph on 6 vertices. Okay, so here is what I'm going to do. I'll try to, okay, so I want to know, so the new graph is going to be on degree small d squared. So the graph is going to be on vertex set n1. Okay, so sorry, this should not be n1, n2. This should be n1 times d or n times d. What is n1 here? On nd vertices, but the degree is just small d squared. Okay, so I'm going to tell you, if I start off with a vertex that is u comma a, and I ask you to go to the I1 comma I2th neighbor, how are you supposed to figure out which vertex it is? Okay, so I'll just tell you pictorially what it is, and then we'll slowly sit and analyze this. Okay, so what does u comma a even mean? So u comma, I'm going to call this the cloud of u, because every vertex u in G now corresponds to a cloud which is like a copy of H or copy of G2. Okay, so u comma a refers to the vertex corresponding to A inside that cloud. So let's say this vertex happens to be u comma a. Okay, now I want to know what is the I1 I2th neighbor of the vertex u comma a. So here's what I'm going to do. I'm just going to give this to you as an algorithm. Like, how do you compute the I1 I2th neighbor? The first thing is, you are inside the cloud, your label is A. Okay, that's the inside your cloud, that's what your label is. Take the I1th neighbor of A, which means it's an I1th neighbor inside the graph G2. Okay, so maybe this is the I1th neighbor. Okay, now once you end up at a vertex, there is a single what is it called? Intercloud vertex that is emanating from that. Okay, so I'm going to end up taking that intercloud vertex. Now I land up at something. I don't know what this name of this vertex is. Maybe this is something that's called V comma B. Okay, and now I ask, what is the I2th neighbor of B? So that may, I don't know, that may be something. This is the I2th neighbor here. Okay, and now I will say the I1 I2th neighbor of u comma a equals this vertex. Okay, seems like a mouthful, and it seems like a crazy graph to even think of. Sushant, did you have a question? Yeah.
So how are you constructing the intercloud edges or intercloud?
So the intercloud edges were whatever were edges inside the graph G. So the graph G, U was one vertex in the graph G, V was one vertex in the graph G that was connected by an edge.
sorry, but we have G1 and G2, right? I'm not sure what.
Yeah. So therefore, so in the graph G, there is like, I mean, the vertex U has 6 edges going out.
Okay.
Right? And it just so, I mean, the picture I drew it in such a way that, the intercloud edge connecting whatever this cloud and this cloud was coming from this particular vertex inside. I mean, it's like what happened in the replacement product. So there was an edge, this edge was going out, but it's like as if now this vertex is responsible for that edge.
Okay, so the zigzag graph is something similar to a replacement product.
Yeah, except that the edges in the
edges.
zigzag graph are not what the edges you see in the replacement product.
Right. Okay, it's a zigzag sort of thing.
Yeah, it's like every edge in the zigzag graph corresponds to like a zigzag sort of path in the replacement product. Okay, so let's just write this down properly. So what do I need to do? So first thing I need to figure out, let's say I first need to figure out, okay, let's write this as an algorithm. Okay, let gamma G2 of A comma I1, let this be equal to B. That's what was saying that when, oh, that was not B, what I didn't give it a name. So let's call this as
A prime.
Let's call this A prime. Okay, and so this is A prime. Okay, now gamma of U G1 comma A prime, this is equal to B. This is like saying A prime is actually a vertex label in the graph G2, but I can think of that as an edge label in the graph G1. So it's like saying that vertex is responsible for this edge. So I take the corresponding edge, so I end up at V. Okay, and in fact, I might end up at or rather, instead of gamma, let me put a rotation mark here. I'll end up at V, but maybe via its Bth edge. Okay, and now I basically do gamma G2 of B comma I2. This is equal to B prime, and therefore, whatever, gamma G1 zigzag G2 of U comma A at I1, I2, this is equal to B comma B prime. So is the description clear?
Yeah, so both of these I1s and I2s, they are to do with G2. They have nothing.
They are to do with an edge label in G2.
All right. So I think it would be better to call them IJ, because I was thinking the I1 has something to do with G1 and I2 something to do with G2.
Oh, okay. So then, okay. Okay. So let me correct as much as possible. I comma J, and this is just I, and this is J, and this is I comma J. So by which what we mean is that this edge going out, okay, the picture has gotten ugly, but in the notes when I put it up, I will clean up the picture and then put it up in the notes. But yeah, but you're right. So the important point to keep in mind is that when you want to take a neighbor out of a certain vertex, the G edge that you take is not in your control, because you're only specifying which whatever G2 neighbor you're choosing and which G2 neighbor you're choosing at. So you are somehow forcing this to determine which intercloud edge you're going to end up taking. So that should roughly tell you why the degree of this graph only depends on the degree of the inner graph. It doesn't depend on the degree of G at all. Okay, so this is one way. And okay, so here is just to, for people to internalize this. Okay, suppose H was the complete graph on D vertices with self loops everywhere. Okay, that was the graph H. What would G zigzag H be? Okay, and let's ask ourselves the following. Which of these vertices will be connected to these vertices?
I think all of them.
Exactly. So what this ends up being is that this is actually G tensor, the complete graph. because it's like saying that as long as there is an intercloud edge, every vertex here is connected to every vertex here. Okay, is this observation clear? Hopefully, it should give you some insight on what is happening in the zigzag product. But this is like a baby case for it. Had H been the complete graph on the D vertices with self loops everywhere, then I could have gone from any vertex in this cloud, I could have gone to this particular edge, taken this inter edge out, and then gone to any other edge I wanted. So that's a valid zigzag path. So therefore, every vertex here is connected to every vertex here in this thing. So that will just, if you just think about it for a little bit, it's just G tensor H.
Something is not matching. No, the degrees are not matching. No,
no, why will that not match? The degree here is actually D.
No, it's self loops.
Yeah, so it's D.
Oh, sorry, self loops is D. It's not D.
Yeah.
Okay, good.
So this is what you end up with. So a slightly different viewpoint is the following. I don't know if this is, in some situations, this is actually helpful. So there was an intercloud edge between cloud of U and cloud of V. Okay. Now we pasted a copy of G2 here and we pasted a copy of G2 here. That's what these two clouds look like. Right? So this vertex has a bunch of neighbors. And similarly, this vertex has a bunch of neighbors. What the zigzag does is it puts a complete bipartite graph between all of them. That is, it connects all of the vertices on this left Rajma to all the vertices on the right Rajma. So that is one slightly different way of looking at what the zigzag is doing. Okay, I don't know which of this is the more helpful viewpoint to have, but I mean, it's useful to have multiple viewpoints. I mean, so that one of them is a little more insightful to you. Okay, so after all this spiel about, we're going to come up with an elementary construction and stuff, I seem to have given you an example which looks ridiculously complicated. But trust me, analyzing this construction is surprisingly simple. Okay, that's one of the key advantages of the zigzag product, is that the analysis is really, really simple. Okay, so let's analyze the eigenvalue bound for the zigzag product. Okay, so let's just have a mental picture so that we understand what happens to a probability vector or any vector in general. If I took one step in the zigzag, what would end up happening to this probability vector? Okay, so let's start with a vector x. Okay, and I'm going to break it up into blocks. These are all whatever. This is one cloud, this is another cloud, this is another cloud, etc. Okay, these are all the clouds. So there are whatever size of G1 many blocks, and each block is of length size of G2. Okay, good. So, and since we are interested in really what happens to the orthogonal component, I'm only interested in X that are perpendicular to the uniform distribution. Because I want to know how much does this random walk shrink such vectors, because that's what lambda is. So what does X being perpendicular to uniform distribution mean? This just implies that the sum of xi, this is equal to 0. Okay. Now let's ask ourselves, suppose I just did the first step of the random walk. That is the first, I don't know, zig step or something. That is the intra-cloud step. Okay, that is what happens is I had a certain distribution on all these vertices, but I'm only taking a step inside the cloud. What would happen to this vector? What is the effect of that transformation?
Ramprasad, just to be this one, it's x comma u comma a, no?
Okay, so just let's,
because I is
summation x comma u comma a. This should be equal to 0. Okay, this u is a bad choice. Yeah.
Yeah.
Okay. So I want to know, suppose we just took only the intercloud step. That is, we didn't move from one cloud to the other. All we did was we moved from u comma a to one of the neighbors of a. So it would end up going to u comma b at this point, or u comma a prime. What is the result of that transformation?
It's just like a walk in G2, one step walk.
It's only a walk in G2, which means step 1 walk within the cloud, that's like saying, I don't care about what happens here. This is going to be transformed by whatever was the random walk in G2. This block will be transformed as whatever was the random walk in that G2. This will be transformed according to G2. So it's like saying each block will separately be acted upon by the random walk in G2, because you're not moving across clouds. Like within a cloud, you are just asking what happens there. So it turns out, so what you end up with is often what is called I-tensor MG2. That is, you don't change your cloud at all. Okay, I mean, if you think of what the random walk matrix looks like, it's just going to be, it's like a big block matrix where there's going to be the whatever MG2, blah, 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 till MG2. This is what was going to end up happening. Is this part clear? Like this is one step of the, just the first zig step, which is like, you're not changing your cloud. If you're currently, this is the probability distribution not even a distribution. This is a vector restricted to that cloud. And you're just asking what happens if I now take a random walk inside the graph G2. So something happens there. So that is determined by MG2. Okay, so this is step one. Now what about step two? Take the intercloud. So what will end up happening now?
So it's like a walk in G1 after zooming out and thinking of those clouds as single vertices.
Yeah, but it's not even a walk in G1. Like for instance, just imagine at this point, your vector was putting mass 0.1 on this vertex.
So it's already determined where.
So you have to now go to put that mass on this other vertex.
That's right.
It's just shuffling all the entries of your vector according to the rotation map, in fact. I hope this part is clear. So basically, if your vector x, think of the vector x as basically putting a mass on every vertex. So if you have mass 0.1 here, 0.3 here, after this intercloud step, what will the masses now become? I don't know about the rest of the things, but I know for a fact that this vertex will have mass 0.1. I don't know what I said. And this, whatever mass was here, will travel to this wherever that was connected to. So it's just going to shuffle up all the coordinates of x according to the rotation map. So this actually happens to be the rotation map. I mean, at the moment, it's not helpful in analyzing. We are just trying to get a sense of what is going on here. And then step 3 is again another copy of I-tensor MG2. By the way, I'm sure I will make the mistake. I'm just going to call the second graph as H and the first graph as G. I mean, I know for a fact I will make this mistake. For, let me just say, for G zig-zag H. Okay. So therefore, the nice thing about it is that this M now nicely decomposes into the following 3 matrices. So you first take a step in I-tensor H, apply the rotation map, and then take a step in I-tensor H. This is the matrix that corresponds to the zigzag product. Okay, if we can analyze this matrix, it will be helpful. Okay, so that's what we are going to do. So far are things okay? This part takes a little bit of internalizing, but I mean, I would like to spend some more time on this if this is unclear.
What happened in step 2 again?
So step 2, notice that step 2 is really, I mean, it's completely determined. You have no choice here. That is, if you were at this vertex at the beginning of step 2, at the end of step 2, you will be in this vertex. Right? Because there was a single intercloud edge emanating out of that vertex, and that's what you were forced to take. So if X was putting a certain mass here, that mass is now present at this vertex. So all that it does is just shuffles this around. And in fact, if you look at what the matrix is really the rotation map. Like U comma A will end up going to, I don't know, V comma B. Why did it go there? Because the Ath neighbor of U happens to be the Bth neighbor of V, whatever that edge happens to be there. That's why you moved it there, which is precisely the rotation.
So in
Okay.
matrix notation, it's a permutation matrix.
Yeah, it's a permutation matrix. In fact, it's an involution. Like if something goes to something else, that same thing will come back here. Because if you take the rotation map twice, you end up with where you start. Okay. So, okay, at the moment, you look at this thing and you just see what the hell, how am I supposed to analyze this? Okay, why is this a helpful decomposition at all? And this is where it's going to become helpful that I can write H as 1 minus lambda 2 times J plus lambda 2 times E. I'm going to use this matrix decomposition and just plug it in here and see what the hell I end up getting. Okay, so what would you end up getting? You would end up getting I tensor. Okay, let's just write this down. I tensor J times rotation G times I tensor J. This is one such term we would end up getting, and this term will have weight what? This will have weight 1 minus lambda 2 squared, because there's a 1 minus lambda 2 from the first part and 1 minus lambda 2 from the second part. Okay, that is one term. And then there'll be three other terms that involve this error matrix E. Okay, plus there's going to look like 1 minus lambda 2 times lambda 2 times something that looks like either I tensor J rod G times I tensor E. Okay, and there will be a similar such terms, which is 1 minus lambda 2 times lambda 2, which is going to be I tensor E times rod G times I tensor J. Plus there is a lambda 2 squared term, which is I tensor E times rod G times I tensor E. Okay, you mentally tell yourself, anytime you see an E, it's an error term. We are going to just ignore that. Okay, we'll just bound that using a stupid bound, and that will be good enough for our purposes. The key point is what happens here. Okay, what is this matrix? Now notice, we just said, whenever we take a zigzag with a graph H, the random walk matrix happens to be I tensor H times rod G times I tensor H, where H is the random walk matrix of the graph H. I'm just abusing notation there. Now instead of H, I'm putting a J here. So what should this be?
Complete graph can be substituted.
Right, so this is just the zigzag of G with the complete graph. So is this clear to people? It's just basically we just wrote down the matrix decomposition for an arbitrary zigzag product. This is just one special case of that, where the random walk matrix for the inner graph happens to be this 1 by n everywhere, which is like the complete graph on self loops. Sorry, complete graph with self loops. So this is just the random walk matrix of G zigzag with the complete graph. And we just saw what it was. The random walk of, the G zigzag, the complete graph, is precisely G tensor, the complete graph. And that is something we already understand. We understand quite well. So therefore, okay, so let me therefore write this as, this is just G tensor, the complete graph with self loops. I'll just put a star there to indicate that it's a complete graph. Oh, complete graph on D vertices with self loops. Okay, plus a bunch of terms. Now, what can I say about the spectral norm of this thing? The spectral norm of this is at most 1. Right, because I tensor E, the eigenvalues basically, if you look at any vector V, it's going to be shrunk by, I'm not saying this right. Basically, if you think of an eigen decomposition here, then the eigenvalues are basically 1 times whatever was the eigenvalues of E. E we knew had eigenvalues that are bounded by 1. So all of the eigenvalues here is at most 1. So it doesn't shrink a vector. I mean, it doesn't expand a vector. This is a rotation map, which certainly doesn't increase the length of any vector. Okay. And this also, if I feed it the uniform distribution, it would have not changed the vector at all. So certainly the entire norm of this thing is bounded by 1. It's a stupid bound, but that's good enough because we have some dampening factors on the outside. Okay. So we can just convince ourselves that this is at most, what is the spectral norm of this? What is the lambda of this thing? What are the eigenvalues of G tensor K? The complete graph has the following super cool eigenvalues. There is one eigenvalue at 1. The rest are all at 0. So therefore, this is just going to be lambda of G plus whatever is the rest of the terms. There's 2 of them plus lambda 2 squared. Yeah, it's turning out to be a bit of painful calculations for this. But if you really stare at this and simplify things further, it simplifies in the following form, which is that it becomes 1 minus gamma 1 times gamma 2 squared, where gamma I is basically 1 minus lambda I. Okay. So intuitively, if you only care about the spectral gap of this new graph, it just becomes the spectral gap of G times the spectral gap square of H, which actually seems to make perfect sense because every edge in this new graph looked like you took 2 edges in the graph H, followed by an edge in the graph G. And somehow that nicely seems to turn out as gamma 1 times gamma 2 squared. Okay, this is a calculation you can try and work out. It's not hard, but it's hopefully, hopefully the final answer makes sense that, yeah, this is what you should have expected it to be. That, even if you don't understand what the zigzag product does, intuitively, it feels like every step that you took in the zigzag graph looked like there were 2 steps inside the graph H and 1 step inside the graph G. So maybe, if there is justice in the world, this is what it should look like. And turns out it's what it is. Okay. So this was the final theorem that was proved by Reingold, Badan, and Victorson. The zigzag product is due to them, where they said that if you start off with a graph G, which is a ND lambda 1 expander, and H is a capital D small d lambda 2 expander, then the zigzag product happens to be a ND, D squared, and lambda expander, where lambda looks like this. Or rather, the spectral gap looks like this particular thing. Okay. So for constructing an expander family, since I don't have much time, I'll just show you a demo of how it works. I'll keep it in the notes so that you can look at this later, and we'll do this more in the next class. But hopefully this should intuitively give you an idea that we should now be able to build expanders, like constant degree expanders that are larger and larger and larger with whatever lambda we are interested in. Because basically what would you do? You will push the lambda down as much as possible. Use tensoring to make the graph on many, many vertices. Whenever the degree becomes too large, you apply one zigzag product and make the degree small. And you just need to find the right combination of these tools to get your expander graph. Okay, are there any questions so far? Okay, so let's just look at this demo, and I'll hopefully show you how cool these strongly explicit expanders can be. Is my screen visible?
Yeah.
Okay. Okay. So yeah, this is just Selberg, Margulis, whatever. These are what zigzag products are. So there's some sort of base graph which is called the affine line graph, which looks something. So let me just go to the end. I'm going to run all. Okay. So finally, at the end of it, what we are building is I don't know, I was building an expander family where the number of vertices is becoming larger and larger and larger, but they all happen to be of degree 81. Okay, it's just 9 squared. Prahlad, you're muted.
Flash the recursive construction.
So the recursive construction looks like this. You start off with a graph H, which happens to be, I don't know, a graph on this many vertices of degree 9. And the recursive construction looks something like you square it and then you tensor it and then you take a zigzag, etc. etc. It's some combination of things that you're doing. And I just did it for 100 steps. So the 100th graph in this family happens to be a graph on this many vertices. Okay, and it's an 81 degree graph. So just to put things in perspective, the number of vertices is the 1500 digit number. Okay, that's the number of vertices. But on the other hand, if I just want to know what is the 70th neighbor of vertex number 205, okay, or let's say, okay, this should give it to me in about a second or something. So that vertex, the 70th neighbor, happens to be this. Now notice that, by sort of rough estimates, the number of atoms in the universe, the number of particles in the universe is about 10 power 80. There's just no hope of me trying to write down this graph explicitly. But if all you care about is doing a random walk on this graph, this thing will do that for you. Okay, and and these happen to be pretty good expanders, and this gives you a way of constructing expanders on as many vertices as you want. Like roughly equal to as many vertices as you want. And you can do all your random walks on it and use this to build your samplers, etc. And this is how strongly explicit these strongly explicit expanders are. Okay, there's just no hope of writing down the graph completely, but you can do random walks on it. So anyway, so this notebook will be, I would sort of encourage you to sort of tinker with this notebook, try out different kinds of constructions, see if you can come up with other ways of building explicit expander families, etc. So this just has the same, whatever is there in Madan's notes, it just has that coded up. But you can try out your own thing. I mean, it's free to use the Google Colab thing. Okay, so let me stop here with just an agenda of what happens on Thursday. In Thursday, we are going to use this one particular thing of how you start off with a graph and expanderize a graph, rather than just saying that, yes, we have things like LPS expanders, or we have Margulis expanders. That's not good enough in certain applications. And we'll see one application where starting off with a graph and expanderizing the graph has its merits. And we'll see that in coming up with a really cool algorithm to check graph connectivity due to Raincode. Okay, so let me stop here. Are there any questions?
The notebook is not accessible.
Oh, so, oh crap. Okay, I probably need to just share and give the link. Okay, so I'm just going to add that link on the Zoom chat. And I'll also add it on Academy.
You have to change it to anyone with the link.
Sorry?
Under restricted, you could change it to anyone with the link.
Oh, acha. Oh, okay. So that was my mistake. Okay.
Yeah, we do have the link. Yeah.
Yeah. So this should hopefully work, and yeah, and you can try it out. It's a lot of fun. By the way, there's also a similar notebook for hash functions, etc. I mean, if you like, if you like tinkering with it. I learn things more when when I'm able to make minor modifications. These are things, calculations that it's sometimes hard to do on paper. So if there's a machine to do it for you, well, great. Yeah. Yeah. Prahlad has an air of a person about to make a remark.
No, there was this whole spiel on whether you have to multiply matrices on the right or multiply matrices on the left, which operation. But for the matrices, you are looking at I tensor head and involution I tensor h. It really didn't matter.
Okay, fine. Yeah, because zigzag here, it was like whether you zig from this end or that end, it's the same.
No.
But yeah. But yeah, you can't please everybody. Okay, so if there is not much else, let's I'll just stop the stream. We'll see it. I mean, so we'll meet on Thursday. I'll add the notebook on